This video is to address challenge for automated discovery of temperature-dependent structure change. This challenge is about neutron powder diffraction experiment as a function of temperature. It contains two-dimensional data, intensity as a function of d-spacing and temperature. Question 1. Structure transition temperature. We first calculated Pearson correlation function between nearness label temperatures. Then we use wavelet transformation to find the peak locations in the temperature-dependent Pearson correlation function. Our algorithm found 4 peaks corresponding to 4 possible phase transition temperatures. We also calculated a two-dimensional Pearson correlation map to better visualize the results, where we can see clearly color change at these possible phase transition temperatures. Question 2. Signal in region interest as a function of temperature. We first use the dB scan to determine the background region and the signal above background region. From the signal region, we can easily determine the width of the signal and the center of the signal. From the background region, we did a global fitting to determine the background level as a function of temperature and the d-spacing. Then the background was removed from the raw data. Therefore, the integrated signal intensity is simply a sum of the signal in the signal region. Question 3. Information for all peaks at one temperature. We used wavelet transformation for peak finding. The diffraction peak has an asymmetric peak shape with more data points in the high D range side. Therefore, we used an asymmetric wavelet for peak finding. At the same time, the data has smaller noise level in the low D range and a larger noise level at the high D range. Therefore, we split the data into 2 segments and use different criteria for peak finding. After the first step, there are still many false peaks. Use these found peak location as an input. We did a low bill fitting in step 2, during which the peak width was parameterized as a function of d-spacing to reduce the fitting parameter. As a result of the fitting, we generate a peak table with peak location, peak width, and peak intensity. In step 3, with the background as a reference, we remove the peaks with low intensity from the peak table. Question 4. It has 2 parts. In the first part, we need to estimate the likelihood of a phase transition between 2 adjacent temperatures. First, we use dB scan to determine the region of signal above the background for each of these 2 adjacent temperatures. Then we calculate the numbers of shared and unshared signal bins between the 2 temperatures, as you can imagine. With more shared bins, it's less likely to have a phase transition, and with more unshared signal bins, it's more likely to have a phase transition. In contrast to question 1, only the data from 2 temperatures are used for calculation. For the second part of question 4, we need to generate the peaks for all peaks within 5 seconds. We haven't solved this challenge.